Can I get a show of hands before we start who would like me to go over this slide again from a couple lectures ago? Hand up for yes. Hand up for no. All right. I'll do that. And I'll get started a minute early because it's review. So recall one of the goals or one of the kind of uses we were thinking about for logic was coming up with a pacman agent that can plan its way to a goal or can figure out various facts about where it is and what's going on. To do that, we have this tool, the language of propositional logic, and we have some world, pacman. And we need to somehow represent everything that the agent needs to know about the pacman world in the language of propositional logic. So propositional logic has Boolean variables that can either take a value of true or false, and it has possible worlds that assign values to variables. And it has these symbols, these connective symbols that make up a language that allow us to write sentences that allow it to reason about facts about the world that it's in. So we make this variable like at 3317 to mean pacman is at location 33 at time step 17. And this is going to be the truth or falsity of that variable is going to have all these sorts of relationships and entanglements with other variables, like at 3316 and other facts about what happened in between them. So there's a lot of variables to keep track of, and so it's helpful to have kind of crisp strategies for making sure that the connections between the variables match up to what we want the agent to understand. So this was just one slide, and if you're, obviously this is only one small piece of how you give an algorithm knowledge about PacWorld. But you can look at the other slides to see how we encode other forms of knowledge in logic. But just for this one kind of small piece of knowledge that we want pacman to have, how does the variable xt, which is going to take a value of true or false, how might it change over time? How might that depend on other things that happen? So this is a kind of general framework for constructing sentences that can constrain what an agent with this knowledge base can believe. So the general format is something's true at time t if it was true at time t minus 1 and nothing made it false, or it wasn't true at time t minus 1 but something made it true. Two things to check. These symbols correspond to what I just said in English, and what I said in English is accurate and complete. If those two things pass your check, you can see, okay, yeah, that makes sense. This was a way of writing a sentence in propositional logic that captured the content of the statement I just said in English. X is true if and only if, that's what that means. Either both sides are true or both sides are false. This or means that it was either this or both. And so here it is in an example. One way we might construct the sentence to provide to pacman so that it has knowledge about its world is as follows. You will be at location 33 at time step 17 if and only if you were there at time step 16, one of the following two things. So this is the outermost symbol here, this or. So it's either this or both. You are at location 33 at time step 16, and it's not the case that you moved north at time step 16 without a wall blocking you, or it's not, or let's see. Neither is it the case. It's a little hard to read all together. It's easier to break it into parts, but I'm trying to do it all at once. Neither is it the case that you moved east and were not blocked by a wall. Neither is it the case that you moved south and weren't blocked by a wall. So all of these things are ways that this state variable could have changed, successful moves in various directions, and this is saying none of those happened. So either you were there at the previous time step and none of these ways of changing where you were happened, or you weren't there, you were just to the south and you moved north and weren't blocked, or you were just to the west and you moved east and weren't blocked, or so on. So this is the strategy you can use. There are other ways you could write this, but this is a good general strategy, and then you can fill in the details for the sort of, for encoding the sort of knowledge that you're going to want pacman to have. So here's another question for you guys. How might we give pacman knowledge about what the value of this variable is going to be? This variable meaning there is food at location 33 at time step 17. Well, we'll probably want to write something that says either there was food there before and he didn't eat the food, or there wasn't food there before and someone put food there. Well, given what we know of pacman, this doesn't happen, so we could cross this off. So we really only need this one. Food is there if and only if food was already there and pacman wasn't also there. So maybe you can think through, or you can try to write down for yourself as an exercise how you would write that entirely in propositional logic. I think I did most of the work, but obviously it has to be in symbols, not in English. So that would be if you were, I think in what I showed you, I didn't make any mention of food. And so if you're expanding the world to include food that gets eaten, then you'd need to put in sentences like that. Any questions about this or any other topic from the last two lectures before I move forward? I know it's hard to sometimes it's hard to know what to ask, but if you scan through previous slides, maybe. Yeah. Sorry, say it again.
Why would you use the not as 33 as 560? Because if pacman is as 33 locations, it cannot be.
Yep, that's right. It turns out you can simplify this and make it shorter. You can cross this out because this is obviously going to be true if that's true and this is true. So yeah, when I mentioned the food example, I mentioned you could just cross this off because it's never going to be relevant. Similarly, you could cross this off because it's never going to be relevant. You could do that all in your head, or you could write the long version down first and make it shorter later. Sometimes these things get like a little tricky to debug, and they're hard to discover errors that come up, so you can always just play it safe and follow this format. But yeah, if you recognize that something can be removed without changing the meaning, go for it. Other questions? Okay, I'm going to get started. And if you do have questions, if you do have other questions, you feel lost, please do attend discussion section and you can have some one-on-one time. Okay, so last we spoke about partially observable pacman. So this is pacman who doesn't know, we haven't told pacman where he is. In the planning problem, I showed you those videos where he's avoiding the ghosts. We did tell pacman where he was. We told him his goal, and he figured out a plan. Slightly different setup here. We haven't told pacman where he is. We haven't given him a goal, like a goal to get somewhere. We're just having him try to figure out where he is. So the variables are things like the walls, where there's a wall at 0, 0, or there isn't. There's a wall at 0, 1, or there isn't, depending on whether those variables take the value true or false. Whether pacman is blocked to the west at time 0, and so on. Whether he moves west or north at time 0, where he moves at time 1, and so on. Whether he is at a given location at a given time, for any given location, for any given time. Whole lot of variables there in the ... And then he has a sensor model, which says kind of what these, so maybe he has a sensor that we're calling blocked to the west at time 0. This becomes true if he is blocked to the west at time 0. And so that's going to have implications about these other variables that tell us about the world. So if he's blocked to the west at time 0, then either he's at 1, 1 at time 0 and there's a wall at 0, 1, or he's at 1, 2 at time 0 and there's a wall at 0, 2, so on. For every location, there's a clause here. There's also a map. Where are the walls? So we can tell pacman where the walls are to help him figure out where he is. And then we tell pacman some details about the initial state. He's definitely somewhere. And then we add some domain constraints, like there's only one action per time step. So if west 0 is true, then north 0 is not. If west 4 is true, then east 4 is not. And a transition model. That was what I was showing you just now, how the state variables change or how they don't. How state variables change depending on the actions taken, to be more specific. Okay, so here's a demo of localization that I showed you. I'll show it to you again. If he perceives this, then this, that's like him perceiving block to the north at time whatever is true, and block to the south at time whatever is true. So then he can determine that one of these things is true, and so on. So percept is this. These are all the options left. So when you see this percept combined with all the rest of the knowledge base, that entails at 1, 2, 3, 4, 5, 6, 7, 10, whatever. Call this 7, 10. At 7, 10, 0 is false, because that would it's not consistent with the observations he made. So all these places where pacman isn't, you can prove from the physics of pacman that's been encoded in the knowledge base, plus these plus this percept and that percept, you can bundle them into one, being true, and not being blocked here and not being blocked there. All that collectively entails you can prove he's not there. Same for here and there and all these places. Okay, then he moves west, moves in all these ways, and you can rule out more and more possibilities for where he is, for where he might be. So finally, after those actions and those percepts, there's only one location that's consistent, and you can logically deduce it given the facts about PacWorld plus the facts about the sensors and actions. Next example is using logic to answer a different question. Not where am I, not how do I achieve some goal, but what does the world look like? So without loss of generality, let's just kind of rename our coordinates and say that the initial location is 0, 0. Now what's nice for this setting is the percept tells pacman which actions work, so he always knows where he is. This is called dead reckoning. Let me explain what I mean by that. Sometimes when he moves north, he stays put if there's a wall there. So if he moves north and sees a wall there, he knows he stays in the same location. If he moves north and sees that there wasn't a wall there, then he knows he's moved 1 square to the north from where he was before. So he always knows for sure where he is relative to his initial location. It's not a given. And I think, I'll give an example later where it doesn't work this way. So we initialize the knowledge base with pac physics up to t's time steps. We tell pacman you're starting at 0, 0. This is more of a definition than a fact in this case. And then we run the pacman agent for t time steps. At each time step, we update the knowledge base. We clarify which action was taken. We add a sentence saying, at time step 4, the action was west. This corresponds to just adding the symbol W4 to the knowledge base. W4 is true. And we add to the knowledge base new percepts. So like pacman was blocked to the north at time step 3. We add that into the knowledge base together with other sentences that'll entail various things that we're interested in knowing. And then for each wall variable, there's a wall at x and there's a wall at 0, 1, there's a wall at 0, 2. We check to see whether we can prove that it's true, whether the variable is entailed, or we can prove that it's false, whether or not the variable is entailed. And if either of those happens, we add it to the knowledge base. So if we're starting at 0, 0, and Pacman is blocked to the west, then that will imply, given what we know about how its sensors correspond to the world, given what, and more precisely, given what the knowledge base knows about what the sensors imply about the world, then the knowledge base then we can deduce using the knowledge base and those sensors, those sensor variables, that there is a wall at -1, 0. So that would be following the implications from the knowledge base. And then we choose an action and we repeat. So the wall variables are basically the whole of the map. So here's a demo. We start out here. The percept is block to the west, block to the west, true, block to the south, true, block to the north, false, block to the east, false. Okay, so there are walls there, and there aren't walls just above and to the right. And now the action is north. Okay, so now we know that Pacman is going to have moved north relative to his initial location because he wasn't blocked. And now this is the percept. Those four variables, those four Boolean variables, are assigned true or false because we've seen this one's true, this one's true, this one's false, this one's false for the question of is there a wall there? Whoops. Okay, so then we can add walls there. And now let's say he moves east and sees that. Then there have to be walls there. And so on. So Pacman has built out a map because he knows where he is relative to his starting location. He knows what he sees, and what he sees has implications about what must be out there in the world. Those implications are written down in sentences in propositional logic, so we can use algorithms for deducing conclusions from a knowledge base to generate new knowledge, essentially. Yeah?
In the first section that we saw the logic, we said if pacman is in 1, 1, we also should mention that we saw the 1, 2, 1, 3, 1, 4.
Mm-hmm. So in the first step, we would know he's not in those locations, but we wouldn't know where the walls are. So we'd know some facts, but not if we're interested in the particular question of where the walls are. That's one fact where we couldn't deduce one way or another whether there's a wall at 2, 3. Yeah. So he gets percepts. Let's see. I don't have a slide in this slide deck for it. But when you're in the world, you see things, right? So you don't have to try walking through here to know that there's a desk here because you can see it. So if you were to try and write code for something that took in similar inputs as you and learned things, you could give it access to the fact that you're looking at it and you see something right there. So we tell it. That's how it knows. We tell it when it's in this spot, we tell it that there's a wall to its south and a wall to its west, because that's the sort of information that you might have if you were there. We could tell it the whole map, and then it wouldn't be interesting to try to have it figure out the whole map. But sometimes in the real world, we have an agent where we can tell it some things, but we don't have the wherewithal to tell it everything, and we want it to tell us some things that it learns along the way. Where the walls are right next to it. So this is it's a toy problem. I mean, obviously no one needs this for economically useful purposes, but you can use the methods that you need to use in this toy problem for more elaborate problems in the real world. And the idea behind the toy problem that makes it interesting is, suppose we have an agent where we can give it some facts about the world, but not everything that we're interested in knowing, because there are some things we don't know. Can we have it deduce the things that we don't know for itself from the things that are easy to tell it about? So in reality, it's no easier to tell Pacman about the close walls than all the walls, but we pretend it is so that we have an interesting problem, so that we develop good methods that we can use in more interesting settings. Okay, maybe that was more of an elaborate answer than I needed to give, but I hope it was helpful. Any other questions? Yeah? Exactly. Yep. That's what we decided to make this problem interesting. Yeah, you could set up a different problem where it perceived more. I mean, when I was showing you the planning problem where he's trying to figure out a path through the world to eat all the food without the ghost, we decided it's an interesting problem to tell him where all the walls are, but not what path he should take, and he deduces what path to take. And he's done something cool and interesting. Okay, I'm going to move on. All right. So I told you about Pacman figuring out where he is, if he knows where the walls are. I told you about Pacman figuring out where the walls are, if he knows where he is. But you can actually use logic to do both at the same time. You don't know where you are, you don't know where the walls are, but you can figure it out. You can figure both things out simultaneously. And dead reckoning, where you know where you are relative to your starting location, doesn't always work in the real world. So let's consider another Pacman example where he's given less information. Not because it's too hard for us to tell him, but just because it's an interesting problem with some real-world relevance. I mean, the methods we'll use to solve it might be more broadly applicable in real-world domains. So in this case, the sensors just count the number of adjacent walls. Is he next to 0, 1, 2, or 3 walls? Or 4 walls? I think that's a possibility. Okay. So it's a little more than 2 bits of information. Now he doesn't know which actions work, so he's lost. So he moves north. Is he 1 north of his initial location, or is he still in the same place and blocked? Could be either. So how does he build a map? He doesn't know where he is. And likewise, how does he localize himself if he doesn't have a map? It turns out he can just kind of bootstrap his way up. So let me give an example before I tell you how to do it in general. Let's say I start here, and I see that there are 2 walls around me. I don't know where they are, but there are 2 walls. And then I take the north action, and there are still 2 walls around me. So maybe I haven't moved. Maybe I'm still in the same spot, and one of those walls is to my north. Or maybe I've moved, and there are 2 walls to my east and west, just as there were before. So there are 2 possibilities. But then let's say I take the south action, and now there are 3 walls around me. If I wasn't blocked, the first time, then I would move north, I'd move back south, I'd be back to where I started. It couldn't possibly be the case that in the first time step there were 2 walls around me, and in the third time step there were 3. So it must have been the case that I was blocked to my north the first time, and that's why the number of walls around me stayed the same between the first and second time step. And then I moved south. I wasn't blocked to the south. I'm in a new location now, and now I'm perceiving 3 time steps. I didn't have any text associated with that example, so sorry if you got a little lost in it. But if you did follow it, that's an example of how you can still put these facts together and learn things about both what the map is and where you are. Yeah. Exactly. The move north action should be interpreted as an attempt to move north, which will increase your y coordinate by 1 if there's no wall there, otherwise keep you in the same spot if there is. Basically, yeah. So that's why this is intricate. It's hard to get off the ground. But you initialize your knowledge base with pack physics for t time steps, starting at 0, 0. You run pacman for t time steps, and at each time step, you update the knowledge base with you tell it what actions you took, what you perceived, and you check. Maybe, like in the example I showed you, that I walked through, literally, there are things you can deduce about whether there's a wall at location XY or whether there's not. In some circumstances, you won't be able to deduce either. Neither of these will be entailed by your knowledge base, plus your actions, plus your percepts. And likewise for these variables, am I at XY at times t? And you choose an action to get to the next time step, and you keep going. And in many settings, I'm sure you can design some where you never learn anything, but in many settings, you can slowly build the map and figure out where you are together. Okay, that's it for the pacman examples with propositional logic. I'm going to show you one more algorithm for theorem proving in propositional logic, and then we're going to move on to first-order logic. So far, the algorithms that I've shown you for figuring out whether a sentence in propositional logic is satisfied is, actually, I've just shown you one algorithm for that. DPLL, you take a sentence in conjunctive normal form. That's this. So these, you have a bunch of ands, and then clauses that are connected by them, and then each clause is a bunch of literals with ors connecting them. And DPLL will answer whether or not there is an assignment of values to variables that makes the whole sentence true. I also showed you a theorem proving algorithm, and it only works on a certain kind of knowledge base, where all the sentences in the knowledge base have the form A and B and C implies D. Or yeah, basically that form. There's no nots allowed, or they are just single variables being true, like A is true. So that was the only kind of theorem proving algorithm that I showed you. DPLL is a model checking algorithm. You're looking for assignments of values to variables that make the sentence work, rather than following implications abstractly. So this is a theorem. This is a theorem proving algorithm, which also has the property that it can find a contradiction if one exists, and if one doesn't exist, then it's satisfiable. Then there exists an assignment of values to variables that makes it true. So the first thing to note, every clause, this disjunction of ors in CNS form, can be written in this way. A conjunction of symbols implies a disjunction of symbols. So conjunction means and, disjunction means or. So for example, if we have this clause in our CNF form, A or B or not C or not D, that's the same as C and D implies A or B. And you can think about this as, if C and D are true, well, one of these has to be true. If C and D are true, then it's not this one, it's not this one, so it must be one of these. So C and D implies A or B. These are two ways of saying the same thing. The resolution inference rule takes two clauses that we know to be true, and since these are joined by ands, any two of these clauses we know them to be true if the sentence is going to be true. And then we resolve complementary symbols. So here are our two clauses. A and B and C implies U or V. D and E and U implies X or Y. And then we can write a new sentence. And if these sentences are true, this one will be true. So we haven't done any assignments of values to variables, but we've kind of written new knowledge. If this is true and this is true, then this has to be true. The reason is that, let's say A, B, C, D, and E are all true. Well, then A, B, and C are true, so one of these is going to be true. Either it's this one, and so then it's satisfied, or it's U. If it's U, then these three are all true, so then it's got to be one of these. You can check that in more detail on your own time. You can take my word for it if you like. If this holds and this holds, then this holds. And we can just keep, and it's also in the right form. So that's nice. It also has this conjunction of symbols implies disjunction of symbols. So we can keep doing this. Anytime one and only one symbol appears in the conclusion of one clause and the premise of another clause, we can smash them together and get this out. And we can just keep doing this until there's nothing left to do. And the result is, if the sentence is unsatisfiable, if there's no assignment of values to variables that makes the original sentence true, then we will eventually get this. Awesome. If there is an assignment of values to variables that makes the sentence true, then we will never get this. So that is a complete algorithm for propositional logic. I haven't come close to proving this for you or even really giving you any intuition for it. You'll have to check in the textbook for that. Unfortunately, it takes exponential time. Of course, it takes exponential time. Deciding the satisfiability of a Boolean formula like this is NP hard. So if it didn't take exponential time, we'd have a major result on our hands. So it's slow, but amazingly, it will give you an answer eventually about whether there is a satisfying assignment of values to variables. And it does that all without ever really internally saying the sort of thing DPLL says, like, okay, well, maybe A is going to be true. Let's see what the other variables have to be if that's the case. Maybe A is going to be false. It never deals with the models. It just follows rules of inference to get to a conclusion. I haven't told you much, so maybe there's not much to have questions about besides the question of like how, why, and I don't have time to answer that. But are there any questions? Yeah.
So in the example, you have like a common variable u, like in the implied thing on the right, and on the left, and I cancel it out. Like how does it work?
Yep. Okay. That's right. There has to be only one. You can't do it with multiple at a time. Okay. Yep. So you have your set of clauses, and any pair of them could be combined into another. So that's going to be x squared, possible steps. And then you're going to have x squared, order x squared possible clauses, and you can combine any pair of them. So that's going to be another x to the fourth possible steps. And then what are we at? X to the eighth or x to the sixth? X to the sixth. It doesn't end up being quite that bad because it would go to infinity, but that's an intuition for why, 1 plus x squared plus x to the fourth plus x to the sixth, even if the coefficients are going down, it's going to get you something exponential. There's some intuition. Otherwise, I'd have to give you a proof, and I don't have slides for that. Sorry. Okay, any other questions? Cool. Okay, so summary for propositional logic, and then we'll get on to first order logic. Logical inference, what we're in the business of when we're doing logical inference is computing entailment relations among sentences. So we have a sentence or a set of sentences, and we try to figure out, does that entail another sentence? Is it the case that every possible model that would make our initial sentences true also makes this query true? If so, that query is entailed, and we can conclude it. Or we follow rules of inference, but that's what we're trying to discover. We're trying to discover whether some question that we have is entailed by what we know. So theorem provers apply inference rules to sentences. So forward chaining applies modus ponens to definite clauses. That goes in linear time. If we have A and A implies B, we can add B to our knowledge base. Resolution, what I just showed you, is complete for propositional logic. It works for any sentence, any knowledge base, but it's exponential time in the worst case. SAT solvers, based on DPLL, provide very efficient inference. They do it through model checking. And logical agents can do localization, mapping, simultaneous localization and mapping, or SLAM, planning, and many other things, and they all use one generic inference algorithm on one knowledge base. There you go. Okay, first order logic. I think, well, yeah, I'll pause for questions on propositional logic, but I know it's a very broad recruit for questions. Okay. So, we started the course with atomically represented states. We were doing uninformed search. We have state 1, we can get to state 2 or state 6. Do we know anything about state 2 or state 6? No, we just have names for them. That was an atomic representation. In propositional logic, we moved to a factored representation. And the factoring is the variables, the Boolean variables. So the kind of state of the world is completely described by the values, true or false, that all the variables take. So each of those is a factor represented by true or false. We could imagine it as a bit vector. A factored representation is you're basically representing something with a vector in general. And now we're going to talk about a structured representation of the world. So search, game playing, planning, propositional logic, Bayes nets, first order logic, databases, logic programs, probabilistic programs. These are examples of these. And the expressive power of first order logic is going to be vastly more than propositional logic or anything else we're going to talk about in this course, really. So the rules of chess, if you were to write them in propositional logic, would take about 100,000 pages, apparently. You'd have to say that if the knight is in e6 and then it moves, how do you describe the knight moves? Like, if it moves north-northwest, then it ends up in some other square, whatever it is. And you'd have to say that for every possible knight move, whereas in first order logic, we'll see there's a way to say, like, no matter where it is, the position it's going to be in is going to be, you know, the y coordinate's going to increase by 2 and the x coordinate's going to increase by 1. Yeah, question. I didn't write this bullet point, so I can't answer that question. I'm guessing 12-point font, normal page, but I can't vouch for that personally. Okay. Whatever it is, in first order logic, it is 100,000 times shorter. So here's an example of one rule in pacman expressed in first order logic. Okay, some new symbols here. This is pronounced for all. This is pronounced there exists. Or sometimes you say, like, there exists, and then you say such that later in the sentence. So the way to read this is for all t, and t is going to be an object corresponding to a time step. For all t, if pacman's alive at time t, so this is kind of, rather than being a variable that takes a value true or false, this is going to be something that takes an argument, and then it'll be true or false depending on the argument that's fed in. So for all t, pacman's alive at time t, if and only if this whole thing is true. That is, if and only if he's alive at time t minus 1, and there does not exist objects g, x, and y such that g is a ghost, and pacman is at xy at time t minus 1, and the ghost is at time, and the ghost is at xy at time t minus 1. So there's no ghost at the same place as pacman at the previous time step. So this is a way of representing, in a formal language, that rule of pacman. Otherwise, you'd have to go through, you'd basically have to make a sentence in propositional logic for every time step for every location. Questions about any part of that? In particular, the for all or there exists, or what these lowercase letters are, like what this t is, and these g, x, and y. Okay, we'll see some more examples that'll hopefully give you more of a handle on it. So, In propositional logic, a possible world was an assignment of values to variables. Forget about that for this. Sorry, it was a nice, simple state of affairs, but it's not how the world works for first-order logic. Possible worlds in first-order logic are completely different. Here is a possible world of 5 objects that I have drawn. And there will be, so in this slide, there was, whoops. There were kind of these, well, this wasn't a function, but this is a predicate. It outputs true or false. So first I'll tell you about functions. There can be functions mentioned in the sentence in first-order logic, and then the possible world has to define how the function works. So for instance, the left-legged unary function, that is a function that takes 1 argument, in this possible world, when you put this object into the left leg function, it returns this object. When you put this object into the left leg function, it returns that object. So the possible world has to explain how the function works. We also have relations, and they can have arbitrary arity. They can take as many arguments as you like. So this is a binary relation, which takes 2 arguments. It takes an ordered pair of arguments. And a possible world needs to tell you what pairs of objects make the relation true. So this on-head binary relation is defined such that if this is the first argument and that's the second argument, then the relation returns true. If any other ordered pair of objects is input to this relation, then it returns false. Here is the brother binary relation. If this object followed by that object is input to the relation, it returns true. Also, if this object followed by that object is input, then it returns true. Any other ordered pair of objects do not satisfy the brother relation, or when you input them as arguments to the brother relation, it returns false. Binary relation means it's expecting 2 arguments. Unary function means it's expecting 1 argument. We have the person unary relation. So this is a way of saying that that's a person, and that's a person. So a person, the relation will take 1 object from our possible world. It'll return true or false. The possible world needs to tell us which objects is it going to return true for, which objects is it going to return false for. And here I've shown you, it returns true for these objects, it returns false for these objects. Then we have the king unary relation, only returns true if that object is input. Crown unary relation, same idea. We can also have constants. Constants are really just another kind of function, but they take no arguments. So this John constant, or John function, it takes no arguments, and it points to a specific object. Same for the Richard constant. So if a function or relation or constant is mentioned in the sentence, then the possible world for it to allow us to determine in conjunction with the sentence whether the sentence is true, the possible world is going to have to say, how many objects are there? How do the functions work? When I input this, what does it return? When I input that, what does it return? How do the relations work? On which objects, or pairs of objects, or triples of objects, do they return true? On which do they return false? So a possible world is not just about assigning values to variables. It is about enumerating the objects and defining the behavior of functions and relations on those objects. Oops, I didn't finish the sentence. If a function, relation, or constant is mentioned, then the world must have objects, and it must have definitions of those functions, relations, and constants. This is a much richer possible world than merely a vector of trues and falses. What I'm calling a relation here will also get called a predicate sometimes. There's a subtle distinction that you can use if you like, but don't worry about it for now. You can just say they're the same. Okay, here's another depiction of possible worlds. here's a sentence that we have, and we want to know what possible worlds we can combine with it to decide whether the sentence is true or false. So this, you can read it as A knows the BFF of B. This is a function. It takes an object and returns another object. This is a relation. It takes objects and it returns true or false. So that's the first thing to note. These are constants, A and B. You can also think of them as functions that take no argument. What? Okay, so a possible world for first-order logic consists of a non-empty set of objects. Let's call them 1 and 2. For each k-ary predicate, that is a predicate or relation that takes k arguments, here we have one binary predicate. For each k-ary predicate in the language, a set of k-tuples of objects for which the predicate is going to return true if it gets one of those k-tuples. So this is saying if we get 2 followed by 1, then it's going to be true. This predicate's going to be true. If we get 1 followed by 2, then this predicate's going to be true as well. For each k, so this is just one possible world. You could write a possible world where no ordered pair of objects is going to make the knows predicate return true. It's another possibility. So this is just one possibility. For each k-ary function in the language, a mapping of k-tuples of objects to oppos, so objects to objects. So we have one unary function, which takes one object and returns another object. So we have the possible world has to say, well, what's the behavior of that function when 1 is input? What's the behavior of that function when 2 is input? So there's a possibility. This is saying BFF of 1 is 2, BFF of 2 is 1. How nice. For each constant symbol, and here we have A and B, those are going to need to refer to particular objects. As I mentioned, you can think of them as zero-ary functions. So there's one possible world. A is referring to this one, B is referring to that one. Here's another possible world. There's nothing saying that constants have to refer to different objects. And here you can also see, as I mentioned, the possibility that nobody knows anyone. That's another possible world. So this is a possible world, this is a possible world. The truth of the sentence may well change depending on the possible world that we're talking about. Here's a third possible world. There's not a fixed number of objects in the world. And you can think about how many possible worlds while you do the attendance code there. And I'll also take questions while you guys are doing this. Yeah? Left leg, yeah. So technically, the way it's presented in the textbook, and maybe there's another way of doing it. I'm not familiar with it. There might be problems. Technically, the domain has to be the whole thing, and I cheated. Everything, the function has to be defined on every object, and you can like add kind of imaginary objects to be like a sink that their output can point to. But yeah, to be careful, you kind of have to check that that's not going to break the intuition of things. So technically, yes, it does have to be covered over the whole domain. Maybe there's a way of defining it where it doesn't, or maybe that runs into problems. I'm not sure. No problem. Any other questions about what a possible world is? Yeah. Right. Yep. Functions return objects, relations return true or false. So unary means, so they both take one argument if they're unary, but they're returning different sorts of things. So you can see this is returning an object. This, yeah, it returns true if it's circled and if it doesn't return true if it's not. Yes, good question. How many possible worlds? Anyone raise your hand if you think it's more than 50. So raise your hand if you think it's less than 50. Anyone want to name a number that it is less than? Good, correct. Yeah, there are infinitely many possible worlds because you can just keep adding objects here. This set could be infinite. Okay. Now, how do these possible worlds relate to the sentence? How do we combine a sentence and a possible world to decide whether the sentence is true or false in that possible world? A term, okay, I'll introduce the term term to help us talk about this. A term is something that refers to an object. It can be a constant symbol, like A or B or Evil King John. And the possible world will tell us which numbers that means. So if this is our possible world, then Evil King John refers to this object, as does B. A refers to this object. Okay, so that's one kind of term, a constant symbol. A function symbol, of course, with terms as arguments. Functions take terms as they take objects as arguments, and here these objects are referred to by terms. So BFF of Evil King John refers to, I think we'll get to this actually. Yeah. The possible world specifies the value of the function given the reference of the terms. So if we want to know which object is being referred to by this expression, this function of terms, we first replace this with the object that it refers to. Here, Evil King John refers to 2. And so then we substitute 2 in there, and then BFF of 2. We follow the definition of BFF, which is given by the green arrows, to get to 3. So that expression refers to object 3. And the third kind of term is a logical variable, like x, for example. And we'll get to that more later, but if you remember from before when we said, like, for all t alive at time t, t is an example of a variable. Okay, first we have terms. Now we have atomic sentences, and then we'll get to complex sentences. An atomic sentence is an elementary proposition, and this kind of has the same type as a symbol in propositional logic that can take true or false. Yeah?
So does object 2 have 2 classes?
Yeah. 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 So the sentence, I mean, spoilers a bit, but the sentence B equals Evil King John would return true in this possible world. Yeah. Because, so you remember in propositional logic, we dealt with sentences not thinking about necessarily a sentence in a possible world. So we could reason about, like, you know, if A implies B and B implies C, then A implies C, no matter the assignments of values to variables, right? So we can do similar reasoning about what sentences entail other sentences without ever bringing into our conversation particular possible worlds. So if we had, so often we want to talk about sentences without even having a possible world at hand. So we're not just going to be able to reduce it to the possible world. We want to speak in generality about what the sentences mean, regardless of whether there's 5 objects in the world or 10 objects, whether this relation, you know, works in this way or that way. Was there a question over here? Okay, I'll keep going. So one kind of atomic sentence has a relation at the outside. It has a relation with terms as arguments. These terms will refer to objects once we add a possible world to the mix. So here, this is a sentence we were looking at previously. Let's evaluate whether it's true. So, first thing we do, we replace the terms with the objects they refer to. A refers to 1, B refers to 2, BFF of 2 refers to 3, knows 1, 3. I don't see a blue arrow there, so it's false. The way that knows is defined in this possible world is this set of ordered tuples which satisfy it. So 1, 2 satisfies it, 2, 1 satisfies it, same down here. But 1, 3 is not in that set, so it returns false in this possible world. So it's true if and only if the objects referred to by the terms are in the relation referred to by the predicate. So really the predicate is when it's in the logic sentence, the relation is when it's in here, whatever. And another kind of atomic sentence is an equality between terms. So I mentioned before, B equals evil King John is true in this possible world. Here's another sentence that is true, as I'll show you in a minute. True if and only if the terms refer to the same object, as you'd hope. So we substitute 2 in for B, and then we just keep following. So BFF of 2 is 3, BFF of 3 is 1, BFF of 1 is 2, 2 equals 2, true. Kind of a sad situation. Okay. That was atomic sentences. Now I'll tell you about complex sentences. And these use the same sort of symbols that we saw in propositional logic. The atomic sentences are basically working like the atomic variables. Like the variables in propositional logic had no internal structure. And here they do. But the variables can be connected in the same way as they were in propositional logic. And new ingredients, universal and existential quantifiers. This is a universal quantifier for all. Existential quantifier was that backwards E. So this is read as, for all x, x knows BFF of x. Let's see if it's true. It's true in world W. I need to tell you about how you combine this sentence with a possible world and get out true or false. So here's the procedure. It's true in world W if and only if it's true in all extensions of W. Okay, what does that mean? 1 second. Where x refers to an object in W. So here are the possible extensions of this world W. The extension where x refers to object 1, the extension, okay, let's check whether it's true in that world, and then we'll get to the other possible extensions. So in this extended world, x is a constant referring to object 1. So we substitute x for 1, we carry it through, it ends up true. Next possible world, x is a constant term that refers to object 2. Also ends up true because, well, you can see there's the BFF, they know each other. And third possible world, x refers to object 3. 3's BFF is 1, but they don't even know each other. So it's false. This for all is asking for them all to be true. They're not all true, so the sentence as a whole is false. Questions about this, how the for all quantifiers. These are called quantifiers, and this is the universal quantifier. Questions about how the for all quantifier is defined. Sorry. Okay. Yep.
So that the first thing is false.
So this as a whole is false because at least one, exactly one, of the possible extensions is false. Okay, next up, there exists. Same thing, I think, yeah. Okay, we've just swapped out the for all for a there exists. Works exactly the same way, but now if at least one of them is true, then this evaluates to true. So these are all exactly as before, but the sentence on the outside is true. Yep. Knows 3-1 is false because this possible world includes a definition of the knows relation. The way that it defines the knows relation is with these colored arrows. And what the colored arrows mean is knows 1, 2 is true, knows 2, 1 is true, knows 2, 3 is true, and knows 3, 2 is true, and knows of anything else is false. Yeah, so a possible world has to give a definition of which ordered sets of objects will make a relation return true. Exactly. The BFF, so yeah, the possible world, in addition to just being a set of objects, has to include all the details about how the functions work and how the relations work. In a different possible world, if these blue arrows look different, the sentences would have different truth values. Just like in propositional logic, the sentence A and B is going to take a different truth value depending on the possible world we're in, depending on whether A is false or true or B is false or true. Yeah. Yes, I think there might have been one missing detail, which is not for all x, p of x is equivalent to exists an x such that not p of x. So you move the not into the inside and you flip the for all and there exists. Yeah. Okay, here are some here's fun with sentences. How can we convert these sentences into first order logic? Okay, here's a sentence. Everyone knows President Obama. Here it is in first order logic. For all n, if n is a person, that implies n knows Obama. So this is a, okay, is this, put up a 1 if you think this is a function, and 2 if you think this is a relation. This person thing. Yep, I'm seeing some 2s, maybe a handful of 1s, but mostly 2s. Yeah, yes, it is a relation. This is returning true or false. It had better because only things that are true or false can be on either side of a implies. So this is saying if n is a person, then n knows Obama. Same question for knows. Is knows a function, 1, or a relation, 2? 2. Yeah, I see some 2s. Okay. Everyone knows someone. There's another sentence. How are we doing for time? Okay. For all x, x being a person, if x is a person, that implies that there exists a y such that y is a person and x knows y. There is someone that nobody else knows. Maybe you can try to think for a minute about how you'd write this. There exists an S such that S is a person, and for all n, if n is a person and n is not S, that implies it's not the case that n knows S. This is the very precise way of saying what the sentence in English just said. Okay, more fun with sentences. Any two people of the same nationality speak a common language. So let's define two relations. That is, x has nationality n, x speaks language L. For all x and y, there exists an n. Sorry, if there exists an n such that x has nationality n and y has nationality n, that implies that there exists an L such that x speaks L and y speaks L. So these can, it takes a bit of mental effort to do this, but you can write these sorts of sentences out in first order logic be totally hopeless to try to do this in propositional logic. You can take another look at this sentence that I showed you before, telling us about when Pacman is or isn't alive. So let's talk about the conciseness of first-order logic compared to propositional logic. So Pacman can't be two places in once. We can write this like this. For all x1, y1, x2, y2, and t, if Pacman is at x1, y1 at time t, and he's at x2, y2 at time t, that implies x1 equals x2 and y1 equals y2. If he's in two places at once, those are actually the same place, is another way of saying this. Whereas in propositional logic, he's not at 1, 1 at time 0 and at 1, 2 at time 0. He's not at 1, 1 at time 0 and 1, 3 at time 0. He's not at 1, 1 at time 0 and 2, 1 at time 0, and so on. And this is only if he's at 1, 1 at time 0. I mean, then we have to add more to say that he can't be at 2, 3 at time 0 and 2, 1 at time 0. So that's just one square, one time step. It's much longer than that. So that's what's nice about first-order logic, one of many things. Okay, inference in first-order logic. Entailment is defined exactly as for propositional logic. Even though possible worlds are a whole different kind of deal, entailment is defined the same way. So alpha entails beta if and only if in every world where alpha is true, beta is also true. For example, if we have for all x, x knows Obama, that entails there exists a y such that for all x, x knows y, namely Obama. So in first-order logic, we can go beyond just answering yes or no. If we have an existentially quantified query, that is a query with a there exists in it, we can return a substitution for the variables such that the resulting sentence is entailed. So our knowledge base says, for all x, x knows Obama. Our query is, does there exist a y such that for all x, x knows y? Answer, yes. In particular, substitute y for Obama. So, I mean, this would be an answer, kind of a disappointing answer. Maybe we wanted to know more. Here is a more detailed answer. That's the substitution you make to see that the sentence is true. And some notation, if we have a substitution sigma, we just write alpha sigma, and that means you apply all instances of, the first variable in the substitution with the second variable in the substitution. So if alpha is for all x knows x, y, and sigma is y for Obama, then alpha sigma is you make that substitution. Okay. First method of inference we're going to talk about for first-order logic is kind of a disappointing one. It makes you think, what was the point of all this? We just convert it into propositional logic. This isn't the only way to do inference, but it is a good first thing to think about. So let's say we want to know whether a knowledge base entails alpha. A knowledge base entails alpha if knowledge base and not alpha is unsatisfiable, if there's no possible world where that's true. So we convert it to propositional logic, and we use a propositional logic sat solver to check unsatisfiability. And the trick here, we replace variables with ground terms, and we convert atomic sentences to symbols. So here's an example. Exists an x such that knows x Obama, such that x knows Obama. We convert that. We just pick a new symbol for this x, call it x1, and then we convert that to a single atomic Boolean variable. If we have a for all quantifier, a universal quantifier, for all x, x knows Obama, and Democrat is, and Feinstein is a Democrat, these are in our knowledge base, then first we replace the this x in the for all the different terms that we have at our disposal. So this is we convert this into Obama knows Obama, and Feinstein knows Obama, and Feinstein is a Democrat. And then we convert those into Boolean variables with their own names. Okay, here's a third sentence. For all x mother of x knows x. So mother is a function here. Takes an object, returns an object. So how do we convert this into propositional logic? Well, first we observe that mother of Obama knows Obama, and mother of Obama knows mother of Obama, and so on. Uh-oh, this is going to be infinitely many different sentences. We better stop somewhere. So the real trick is we run a loop for k equals 1 to infinity. We get a set of terms. These are constants, functions of constants, functions of functions of constants, and so on, up to depth k. We propositionalize. We turn our sentence into propositional logic as if those are all the terms that exist. If a contradiction is found, then we halt. Otherwise, we keep going. So if there is a contradiction that can be found, this algorithm will find it. So if the first order logic sentence is unsatisfiable, we will find a contradiction for some finite k. And this was a subtle, this had to be proved. This was proved by someone named Herbrand about 100 years ago. But if it's not unsatisfiable, then this may continue forever. It'll never return a contradiction. We'll keep going, and we won't know whether that's because there is no contradiction to be derived, or because we just haven't gotten there yet. So it's semi-decidable. If there's a contradiction, we can find it eventually, but if there's a no contradiction, we'll just keep looking for one and never know if there's none to be found or if we just haven't found it yet. That's too bad, but it is what it is. Okay. The other kind of inference that I'm going to tell you about in first-order logic, which kind of stays in first-order logic rather than just like getting into some other form of logic that's easier to prove things about, is called lifted inference. And here's an example of lifted inference. I'm not going to give you an algorithm for it, but here's an example of it, dating back a couple thousand years. So if Socrates is a person, this is a unary relation or predicate. If Socrates is a person, Socrates is a person, full stop, that's part of our knowledge base. Second thing in our knowledge base. For all x, x being a person implies x is mortal. You can conclude from that Socrates is mortal. It applies to all people. This is true for all people, so it's going to be true for Socrates, so the conclusion is true, so Socrates is mortal. Makes enough sense, I think, without looking to like possible worlds and all that. So the general rule here that this is an example of is a version of modus ponens. I think it's called generalized modus ponens. And here's how you write it down. It's a bit messy. Given alpha implies beta, so that's one sentence, and alpha prime, that's another sentence, if you can make a substitution to alpha and alpha prime that makes them look the same, then you make the same substitution to beta and you can conclude that. So here we're substituting x for Socrates. And when we substitute x for Socrates, this looks like this. This is in our knowledge base. So now we can conclude this with that same substitution. That's how that works. Or, here's another example. For all x, x knows Obama. And for all y and z, if y knows z, then y likes z. We can make the following substitution to make this look the same as this. Namely, we substitute y for x, and we substitute z for Obama. Then these look the same, so we can conclude likes x Obama. And there was a for all in there, so it's for all x, x likes Obama. Wouldn't that be nice? Sorry, I can't say things like that. Examples. Prolog does this, backwards chaining. Datalog does forward chaining. These are similar to the algorithms that I showed you for propositional logic, but they work with lifted inference in first-order logic. Production rule systems, some production rule systems use forward chaining, and then you can also do resolution theorem provers. So that resolution algorithm I showed you briefly has a kind kind of an equivalent that deals in first order logic. And so we can prove things without ever trying to look, kind of like I was mentioning before, we can do all this work without ever looking at the particular possible worlds in which the sentences are true or false. And that's great because there are infinitely many possible worlds to look at. And even if we're looking at possible worlds with only k objects, there are exponentially many possible worlds to look at, assuming we have functions with at least one argument or relations with at least two arguments. It gets real messy real fast. So, summarizing, first order logic is a very expressive formal language. There are many domains of common sense and technical logic where, knowledge where we can write what we know into first order logic in a fully formal way. And that means we can automate deduction from those facts. So circuits, software, planning, law, taxes, network and security protocols, product descriptions, e-commerce transactions, geographical information systems, Google Knowledge Graph, semantic web, to name a few, are systems where we can encode relevant knowledge in first order logic, and we can have systems that follow the things that we know to their logical conclusions without our help. Inference is semi-decidable in general. We can prove that a sentence is unsatisfiable. We can prove a contradiction, but we can never prove generally that there is no contradiction. So sometimes we can, but sometimes we can't. That said, semi-decidable in general, but many problems are efficiently solvable in practice. And inference technology for logic programming, people have put a lot of work into this, so they've come up with efficient ways that work in many domains. Okay, I've made some quiz questions for you to check your understanding. Stick around for them. We still have another 4 minutes. And I'll show you the answers in a bit. So translate the following sentences into logic. Use intuitively named functions and relations or predicates. Here's an example. Every person knows Obama, as I showed. For all n, person n implies n knows Obama. So try writing these down either on paper or computer, and then I'll show you how I've written them down. In general, I mean, you certainly have choices about what you name your functions and your relations. You have some choices about what objects you're kind of imagining in your world, so there are multiple ways to do this, but try coming up with a plausible one. Take a minute to yourself to do that, and then I will show you how I've done it. Because if you struggle to do this, better to find out now than later. Anyone want to offer a possibility for the first sentence? Yeah. There exists an X, so there, let's see. There exists an X such that person X implies name of X is Steve. Yes, I think that works. I think I've just written there exists an X such that X is called Steve. Another thing I wrote is there exists an X such that person X and that X is a person and X is named Steve. So I had an and here instead of an implies. I think the way you said it doesn't quite work because one way of fulfilling that is that there's no person involved. Because if there's no person, then the premise of your implication is false, and so the implication is true. Yeah, it's really finicky. Yeah.
You have to say like what set X belongs to, or
Your only option is the whole set of all objects. So if you kind of want it to specify, if you kind of want X to only be some subset of your objects, then you have to say there exists an X with the property that's in this subset and whatever else you were going to say. Yeah, basically. Yeah. Okay. Anyone want to offer a way of writing this in logic? Yep. Yes, that's right. I left out that they had to be people, but yeah. If your world includes objects that aren't people, then you'd want to specify, this only applies when x and y are people. But yeah, if for all x and y, x not equal to y implies x hates y. Or others, whatever. And we don't really have time to talk through these, but here's what I came up with for those. You can check to see if they make sense to you. And come up for questions, if you still have them.